So hi, my name is Will. Thank you for waiting. Thank you for inviting me. Did you hear me? This is a bit loud.
It's okay.
Thank you for inviting me. You made a pretty good estimate of what I'm going to be talking about. Not so surprisingly, I guess, because I copied the abstract of my paper into the workshop. So I'd like to start by apologizing. I made this talk last night because of a series of very unfortunate events in the last 2 weeks. And the gods of hotel Wi-Fi were not very helpful last night, and I guess you all know this. So there will be a few, sorry?
Somebody's online. Mute.
Okay, I can continue with my apology, but I hope the next 25 minutes will be still entertaining. I'd like to also start with a little deviation. There was an earlier talk about a nickel oxide, which we have a work that is very relevant, which I'm not going to talk about today, but I'm going to put a little bit of a shameless, a relevant mention of it at the end, because we actually measured ultrafast crystallography of nickel oxide in the magnetic phase, which is directly relevant to the conversation earlier about exchange friction in this material. So without further ado, if this thing will work, which it doesn't, obviously, that would be too easy. Please work. 2 years of no code of, oh, come on. Maybe I take this thing out. Two years of no COVID, huh? Yeah, it's not going to work. Yeah, I will after you wrap up. Hello. So if we were anywhere else, I'd start with a lot of motivations about digital recording, new properties with antiferromagnets, and why we work in the ultrafast. But because this is a workshop on ultrafast antiferromagnetic writing, I basically don't need to do any kind of introduction, which is fantastic and terrible at the same time, because I have lots of time to talk about other stuff. So I just wanted to briefly show this thing, which is a concept that I guess everybody here more or less knows. So I'm just going to remind you. It's the idea of having dissipation-free antiferromagnetic demagnetization, meaning that we don't need to transfer angular momentum to the lattice like in ferromagnets, because oppositely aligned spins can sort of demagnetize into each other, which is one of the promises of antiferromagnets. So I'm just going to say this as sort of an introduction. I find antiferromagnets very, very cool. And they're cool because they come in a really unique zoo of crazy arrangements that like screws, cycloids. This is my personal favorite. This is the helical butterfly structure, which flaps its wings and rotates as it progresses through the crystal. This exists in nature. This is in langasite crystals, minerals. And one of the things that I come across a lot when I talk to people is that they, even if they work with these kind of materials, they don't really know how we know these kind of structures in the first place. And so the more experienced people obviously know this, and I thought that as an introduction, I will talk for about a minute about that. So how do we resolve these kind of crazy spin structures? The answer to that is with magnetic diffraction. And typically, or historically, we have been doing that with neutrons. This is one of the first papers from 1949 of a neutron diffraction experiment on antiferromagnet, where the concept is very simple. You have this kind of beam of neutrons going through a crystal. In this case, it's a polycrystalline sample. That's important. We have our detector here, which is sort of a strip, and we have these powder rings that imprint on that, and we get something that looks like this. What you see here is the counter angle, and you have two panels here, one above and one below the magnetic phase transition, where you see these regular structural peaks at room temperature, and additional peaks form when you go below the Néel temperature. Here's another example of this, which I think is a little more telling. This is a different material, it doesn't matter, where you see structural peaks, and then below the Néel temperature, you see these huge additional peaks, which we use to then solve the spin structure. And an important detail, which will bite us later, is that these peaks are very much comparable in size to the intensities from the regular crystal lattice. So we want to do ultrafast, and neutrons don't come in ultrafast pulses, at least not yet, but X-rays do. So we can do similar science with X-rays. And X-rays are unfortunately sometimes a compromise, because even though we have great new synchrotron sources, X-rays fundamentally are different in how they interact with materials. And so this is an example of this material studied with the exact same wavelength with X-rays and with neutrons, which I copied from this PowerPoint from, I think it's Oak Ridge. And you can definitely see that because of the cross-section of X-rays compared to neutrons, it's harder to study this material than it would have been with neutrons because of this decay in intensity with the ordering wave vector. It's even worse when you work with magnetism, because the diffraction peaks that we saw before that appear below the Néel temperature get this prefactor in their intensities when you work with X-rays. This is on the order of 10 to the -6, which means that magnetic diffraction peaks are typically 6 orders of magnitude weaker at the energies we typically want to work at with synchrotrons. So for that reason, we go to work at atomic resonances, which has had an explosion in use in the last 20 years because everybody wants to do XMCD. I am not going to talk about anything spectroscopic. The reason I'm raising this is because everything I will do will be at a resonance. It'll be at something like 7 resonances. But we only use this to enhance our signals. We do not, at least not in this talk, care at all about spectroscopy. We can discuss this after this talk if anybody is interested. But this is another connection point where people often talk to me about this and misinterpret our intentions. So what do I mean by resonance? This is a magnetic diffraction peak. And when we cross an atomic resonance, its intensity goes from being like nothing to being very intense and then back down to 0. And of course, more is encoded than just more intensity in this. This is the manganese L2 and L3 edges, of course. Again, this is just to emphasize what we want to do. This is one of the slides that suffered greatly from the absence of Wi-Fi in the hotel. And this is another one of them. So this is the technique that we're going to be using. Essentially, we're going to scatter light off of a sample. Light comes in, light goes out. It goes into a detector, which can resolve its polarization. We can control the incoming polarization. And all of the experiments I'm going to be showing today were done statically at SLS at ESRF and dynamically and statically at BESI. All the time resolved work was done at Femtospecs, which is the slicing source for soft X-rays in BESI, which is a lovely, lovely source. We love it, we love it, we love it. So I'm going to talk about 2 things, exactly like you said. I was actually going to talk mostly about this, which I've never talked about before because of COVID. It's a very weird situation where you publish a paper and never talked about it before because of COVID. But since we're in a conference about writing, I thought maybe I'd show this thing, which I've actually shown many times. So I'm going to go very briefly on the specifics here because this talk heavily uses the capabilities of the technique, which I have not discussed in detail before. And I'm just going to try to skip to the essence of things, which are most relevant for everybody anyway. So we have our little model system. This is our model system, gadolinium, rhodium, 2 silicon 2. It's an antiferromagnet with layers of ferromagnetic layers of gadolinium. They're antiferromagnetically coupled to each other. And there's these potato layers of silicon and rhodium in between, which are not going to serve any purpose for what I want to say now. So I'm just going to not even draw them anymore, as you can see here. Same material, rhodium and silicon argon, and we have these layers. Now what I've drawn here is transparent and solid spins in one layer, and the same thing in the opposite layer, just pointing in the opposite direction, and again up here. And I've already drawn this angle, which will become obvious why in a minute. And when we heat up this material, its magnetization, well, its ordered moment or its order parameter weakens until it goes to 0. Another key feature is this curve here, which is this angle here. So what is this angle? This angle shows us that the spin structure, the entire spin structure, not one individual spin, but all of the spins, I'm going to have to wave my hands now. All of the spins rotate coherently as you heat up the system by about 35 degrees. This is a relatively large effect. And here is another view of this. This is now a top-down view. You have the low temperature case where you have spins pointing along or parallel or anti-parallel to that axis. And then the axis shifts to up-down at high temperatures. And what we're going to ask And the purpose will become clear later, is if we can drive the system along this path. Of course, the answer is going to be yes, because otherwise I wouldn't be talking here. And I'm going to very briefly talk about this experiment. This is what it looks like. We copied from the same place. Our pump beam, which is just 800 nanometers, comes in, hits our sample, and we get a Bragg peak from the X-rays. And we want to quench that Bragg peak with our pump, but not too much, so that we actually see this rotation. And so this is what this Bragg peak does. This is many different fluences at a given sample orientation. This makes a huge difference how your sample is oriented with this angle over here, if anybody is interested in the specifics of this technique. To my knowledge, is the first time that azimuthal dependence is measured in the time domain. And what you can see here is that a lot more is happening than just a weakening of the order parameter or just a rotation. There's some sort of superposition of both effects. And with a lot of details that I won't go into, we disentangle the two effects that are seen here statically. One of them is demagnetization and recovery of the, this is this blue line here, when it's statically. And here, what you see is the rotation of the coherent rotation of the entire spin structure. And essentially what tends to be understated is that essentially this is parametrization of a solution of the spin structure at every single delay. So at every single delay, we have quote unquote crystallographically solved the spin structure. And we can say every spin in the unit cell where it points at every single delay for this, in this case, 4 different fluences. And of course, you can see that more is happening than just a shift. So the baseline here is this shift, which we see also statically in equilibrium. And we have this wiggle on top, which is a displacive excitation of the local magnetic potential of every spin, which I will discuss a bit later. So I'm going to briefly talk about what happens at very late delays when we don't have the displacive excitation anymore. So we also solved the spin structure for many fluences at one delay. This is shown here. This is again parametrized by that angle. And we see that we have a linear dependence. And so essentially, if we want to rotate the entire spin structure by a certain angle, we can choose a certain fluence. That is very deterministic and lovely for what some people would call switching or some version of control. You can imagine you can control something like MRAM or something like that with your laser pulse by rotating your entire spin structure deterministically. Now, this is actually a pretty large effect. It's 35 degrees. But if you actually look back in literature, this is 1975, it's pretty old. This is gadolinium metal. This is the anisotropy of gadolinium metal. And turns out that that rotates even a lot more. And this is facilitated by the fact that gadolinium is a half-filled 4F shell. And so it has very weak anisotropy, which is typically imprinted by the conduction electrons, because 4F electrons are not conduction electrons. So one can imagine an even stronger effect if you want to utilize gadolinium. And actually, even though there's a lot of ultra-fast work on gadolinium metal, I've never seen anything associated with its anisotropy. Maybe somebody will do something with that. Right, so I'm going to summarize this very short part by saying what I did and didn't say. So this is what I just showed you. And what I didn't show you is that through this wiggle, and we solve the spin structure for every delay, we can also reconstruct the local anisotropy potential of a spin in real units of energy and angle. And the purpose of this work was to demonstrate the concept of controlling the local anisotropy potential with some means. In this case, this was this thermal means. But this concept is a concept that we believe was relevant to demonstrate in order to present the idea of how to control usefully a antiferromagnetic spin structure with light. So that's shown in this paper here if you want to read more. And I'm specifically, as a diffraction person, very excited about the fact that we can solve spin structures in the time domain, which to my knowledge, this is actually the first time this is really done. Which is exciting to people like me. So, and now I'm going to talk about this, which, like I said, I've actually never talked about before, even though we've published the paper already, which is very weird. So you're my guinea pigs, and we're going to see how that works. So, intro to lanthanides. When we talk about magnetism, 99% of the people talk about these three elements, maybe manganese and chromium as well. But for things to actually work, we typically need a little bit of a 4F system because they have large moments, because we can engineer them, and this makes everything great. And they're very important for almost every application that involves a magnet. I was particularly amused by this when I was trying to Google useful articles on lanthanides. Why rare earth are the key to just about everything. So they're useful in cars and healthcare and energy generation. I heard recently a talk where offshore wind turbines were said to have hundreds of kilos of nickel and cobalt, I think, and they each needed to have something like 20 kilos of dysprosium. So these are actually huge amounts of these materials. And if we want to use them in ultrafast devices, we would also like to understand how they work in the ultrafast time domain. So when we have two 4Fs that want to talk to each other, we want them to interact. But unfortunately, as we all probably know, because we went to physics kindergarten, 4F states don't really want to talk to each other because they're very localized. This is the distance. So this is half the distance to the nearest neighbor in a lanthanide metal. So they don't talk to each other, which is unfortunate. But what they do is they talk to their in-house neighbors, the conduction electrons, specifically the 5Ds, and they polarize them. And these do talk to neighbors, so they polarize the conduction electron cloud. And we get what's called RKKY, which is this indirect exchange, which depends on two critical terms. One is this chi, this is the susceptibility of the conduction electrons. And the second term here is the overlap integral between the 4Fs and the 5Ds, which will be very critical for what I'm going to say now. So the question arises, can we actually have this kind of dissipation-free direct spin-spin demagnetization if our coupling is indirect? If it's not actually that these two guys are talking to each other, but rather that they have these messenger electrons that go through the unit cell until they reach their other neighbor. So the answer to this is yes. And I didn't figure this out, other people did. This is a nice paper from our colleagues in Bessie, who demonstrated that in dysprosium, when it becomes antiferromagnetic, you get an additional faster demagnetization, or more efficient, with the very catchy title, Antiferromagnetism beats ferromagnetism. Very cool. And so the answer is yes, and that's lovely. Now let's do something with that. Can we tune RKKY's strength to optimize our ultrafast dynamics? So if we'd want to tune RKKY, how would we do that? We have these two critical terms here that I mentioned before. So the first route would be to control the conduction electrons. And we are actually actively working on that. That's not so easy to understand, unfortunately. You can tune the occupation at the Fermi level, doping, and so forth. And the second thing that people intuitively talk about, but actually is not easy to do, is to address the on-site overlap between the 4Fs and the 5Ds. Now, how would you do that? One thing you could do is actually change the occupation of the 4F shell, which is also not so trivial to do. So the overlap is directly sensitive to the filling of the 4F shell. So the question I'm going to be answering is, how does the 4F filling affect spin dynamics? This is also a slide that could have been much prettier, because this is the question I'm going to address now. How does the 4F filling affect spin dynamics? And through that, how do we control it? So if we look at literature and we try to find a reasonable comparison between dynamics of 4F systems, we can find these examples. And these are pretty much the only examples, except for lots of optical work on gadolinium. And unfortunately, this is very inconclusive because the conditions of these experiments are extremely different. This is a single crystal. This is a thin film, but it's very thick compared to these guys who are very thin and are comparable to each other. So unfortunately, we can't really easily do that. So what we're going to do is we're going to use this series of materials, which as an aficionado of antiferromagnets, I can tell you that this is a series of the most boring antiferromagnets you can think about. They are very, very, very boring. What we're going to do is we're going to change the lanthanide ion here, and nothing else is going to happen. So this is what these materials look like. The exception in this series is the gadolinium system I showed you before. If you're interested why it's still valid in gadolinium, you can talk to me later. And what happens essentially is that you heat up the system and the ordered moment goes down and goes away almost identically in all the systems, except for this green and red, which I can explain later a bit why. It's a mean field issue. But apart from that, when you say take neodymium and replace it with praseodymium, the only thing that's going to happen is that you get a different Néel temperature. Apart from that, The spin structure stays the same, the magnetic structure, essentially. The crystal structure stays the same, and it's all extremely boring, extremely boring. There's no special phases or anything. So this is very useful for us because we can essentially change the magnetic ion, effectively only change the Fourier filling, which is kind of remarkable. We found a system that's so boring we could actually do that. So this is what our experiment looks like. Shine light in, shine light out at femtospecs at Bessie. We get a Bragg peak, we quench this Bragg peak, and we watch it go away as function of delay. Here are two examples. This is samarium rhodium-2 silicon-2. This is terbium rhodium-2 silicon-2. And you can definitely see that there's a difference in amplitudes and in time scales. This is 5 picoseconds. This is 100. These are differences that appear. And in fact, we pretty much collected a ridiculously large amount of data on all of these materials. I'd like to point out now that I'm expecting a comment from Peter Openier about samarium, because in 2017, I met you in a conference and you told me that samarium has low-lying states that would potentially cause it to be much faster if we directly excite to it. So we repeated everything for 400 nanometer excitation, causing this to be a very, very long experiment of about continuous beam time for 2 months. If you'd sum it all up, this was over about 4 years. With all of these data, what are we going to do? Lots of comparable data, just looks like more of the same. And what do we do with all of it? So of course, what we're looking for is some kind of scaling relationship. So we can look at the amplitudes, we can look at the time scales, we can also look at the fluences, and that's exactly what we did. So here you have amplitudes. They're as function of a normalized fluence, which I'll explain in a minute. Same goes for time scales. These are now time scales that are normalized by a characteristic time scale per material. And you see that the time scales do vary a lot between the materials. So samarium is the fastest, holmium is the slowest. But they all fall in this one curve, which has meaning, which I will not explain because that's difficult for me to explain, but this is a square root. It's in the method. And we have this material dependent critical fluence, which is just defined based on this linear behavior, nothing special. And now we scratched our heads trying to build mountains around these scalings and what could happen there. And at some point, I went to Dresden and by chance heard some guy talk about something that I remembered from my physics kindergarten. And that was the Gen scaling. So in lanthanide magnetism, especially in the 50s and 60s, it was very common to talk about the Gen scaling. So this is the Gen factor. This is a picture of Pierre de Gen from a real paper. I did not just find this off the internet. Well, I found it off the internet, but it's a real picture on a paper. And this is just a quantum, well, I wouldn't say quantum number. It's a theoretical number, which is a function of L and S. So this is just a Landé factor, which is a function of L and S. And this is, of course, J, the total moment. It's also just a function of L and S. And it turns out that a lot of quantities scale with this thing, which is actually nothing but, how it's written here, actually. The average squared projection of S on J. Intuitively, it's how spinny things are, if you will. So here we have the Curie temperature as function of, and here we have this de Gen factor. Here we have the de Gen factor in the x-axis, and here we have the interlayer rotation angle in all sorts of alloys of these materials. Here we have, again, the ordering temperature, and it all points to say that the coupling should, the magnetic coupling should also scale with this quantity, which has also been shown in theory. I went through lots of papers in French from the 1960s. This was not easy because my French is not very good. But turns out that that is really what we want to expect here. So the conceptual understanding that we want to have in the back of our minds is that if we have a dynamic process and some sort of rate, in our case, angular momentum transfer rate, we will have, I'm almost done. It should scale with the strength of the associated coupling. So we're going to define now an angular momentum transfer rate in units of nu-Bohr over picosecond and plot it as a function of the de Gen factor. And we find that it's actually pretty linear. This is for one fluence, all fluences work. And I was very happy with this already. Some of my colleagues were less. So to be clear, if this is our unit cell, This is one layer. This is another layer. I'm talking about this coupling. So our theory colleagues calculated this and found that it also scales with the de Gennes factor, while these guys, which I'm not showing you because I'm lazy, do not scale with the de Gennes factor at all. Also, all the other couplings in the system, they calculated many more. And so the last thing I'm going to point out is that this does not go to zero. This does not go to zero at all. I'm sure and somebody will be upset at me about this, but the key understanding here, if you look at this diagram, is that if you have one 4f site and another 4f site, the coupling goes through the conduction electrons, of course, and angular momentum is transferred through them, but not perfectly. Some of it goes to the lattice. And this is what we see here. This is where this is a rate that does not actually depend on the 4f filling. In other words, it does not depend on the overlap integral between the 4f's and the conduction electrons. So our conclusion from this is that spin dynamics are governed by RKKY, and we can control it with the 4f filling. This is a very simple conclusion, which scales inversely with how much work we put into this, but I think that's kind of necessary. So the summary of this whole talk was the deterministic control I showed you before, the thing I just showed you now with the de Gennes scaling. Here are papers that show these things. The last thing I'd like to point out, some shame, and we can solve twin structures in the time domain, and shameless advertising. We did ultrafast lattice dynamics with electrons on the colloxide. It's directly relevant to the conversations you had before. I think the time scales we saw fit to what you showed in your talk, which is very cool. And I hope you guys find this all very interesting. So thank all these people. Thank you for inviting me and thank you for your attention. I'm done.